Good afternoon. Yesterday we have started discussing the properties of moist air or psychrometrics, and today we will continue with this. Yesterday I have introduced wet bulb temperature, and I have told what is wet bulb temperature, how to measure it. But today I like to elaborate it little bit, bringing a small amount of mathematics. See, a wet bulb thermometer, the construction is something like this. This is the bulb, basically it is an ordinary thermometer, and on this you have got some wet wick, which is this wick is wet with pure water, and then on across this wet bulb. So, the bulb of the thermometer is wet with water, and across this bulb we have got flow of air with sufficiently large velocity. Okay. Then what will happen? I have explained that there will be both heat transfer and mass transfer. Basically, some sort of a boundary layer will grow here, and we will have a variation of temperature, and we will have a variation of concentration, of water vapor. That means, the concentration of water vapor will vary from the outer surface of this wet wick to the air which is flowing past it, and there is a variation of temperature from the outer surface of the wick to the air which is passing past it. And I told that there will be two different transport phenomena. The first one is the mass transfer. Mass transfer means, as the concentration of water vapor is highest, or the air just adjacent to the wet wick is saturated with water vapor, it is having high concentration of water vapor, whereas the air which is passing past it, it is having a lower concentration of water vapor. So, moisture will get transferred from the vicinity of the wet wick to the ambient air. So, as the moisture get transferred, so more and more water will get evaporated, and there should be a continuous supply of water. That is why this wick is connected with some sort of a container. All right. So, when there is mass transfer or continuous evaporation, then it is taking away some amount of latent heat. So, the temperature of this wick will fall, well, but it is surrounded by the air which is having a higher temperature compared to this. So, there will be heat transfer from the air to wick, and an equilibrium will reach after a short while, an equilibrium will reach. That means, energy transfer due to evaporation and energy transfer due to heat transfer, that will be equal, and then we will have a temperature indicated by the thermometer. All right. That thermometer is wet bulb, that temperature is wet bulb temperature. Now, what we can write, let us say the property of air, I am writing PV, the vapor pressure in the air, then omega, that is the humidity ratio of air, H, that is the enthalpy of air, and obviously T is the temperature of air. And here at the outer surface of the wick, the properties of air which is saturated with water vapor will be having a specific volume, partial pressure P v dashed, then specific humidity W dash, temperature T dash and enthalpy H dash. So, I am writing air stream, this is air stream, this is air adjacent to the wick, all right, air adjacent. So, mind that both are the properties of air only, all right. Now, what we can write the heat transfer, what is the heat transfer? Heat transfer we can write heat transfer is let us say the heat transfer coefficient is, again I am using H, but let us use H convection, HC I am using, heat transfer coefficient into area of the wick into temperature of the air stream minus temperature of the wick, all right. So, this is our heat transfer. Mass transfer, again it will be some mass transfer coefficient, this is diffusion mass transfer. So, K d, and then we can have area and P v dashed minus P v. This can be written this can be written as K w A W dashed or omega dashed minus omega. That means, instead of partial pressure I am replacing the humidity ratio. Excuse me. Energy transfer due to evaporation. Energy transfer due to evaporation. So, what I can write is K W A into H F G, this is the latent heat of evaporation, and W dashed W. So, now I can equate energy transfer due to transport of heat and energy transfer due to evaporation. So, if I equate, I will have HCA T minus T dashed, then it is equal to K W A H F G W dashed minus W, or T minus T dashed, A get cancelled from both the sides, K W H F G divided by H C W dashed minus W, T dashed is equal to T minus this K W H F G H C W dashed minus W. All right. So, what one can see that if T dashed is the temperature, let us say this is T dashed indicated, this is actually T dashed. T dashed is the temperature indicated by the wet bulb thermometer. So, that T dashed is less than dry bulb temperature or T. When both of them will be equal? When this quantity is 0, that means when W is equal to W dashed, that means when the air stream which is flowing past the wet bulb thermometer is fully saturated. That is what I have told yesterday also in the psychrometric chart. For on the saturation line we will have dry bulb temperature equal to wet bulb temperature. All right. Now, you see this T dash is wet bulb temperature, and for air water system it becomes also a thermodynamic property, not for other system. That proof also can be made, but I am not doing it here because that needs little bit involved knowledge of mass transfer. So, I am not doing it here, that is not needed for this course, but this T dash then becomes another thermodynamic property for air water mixture. And one can independently measure T dash and T. Let us say pressure is fixed, that means it is atmospheric pressure. So, three different properties are needed. Any other property of the mixture, air water mixture, can be determined, and that is what we do with the help of a psychrometric chart. Well, now we will again go back to our discussion regarding other properties of moist air. One property which is very important, that is enthalpy of moist air. Enthalpy of moist air. Well, see, in moist air there are two components, one is dry air and another is water vapor. So, enthalpy of moist air will be summation of enthalpy of dry air and enthalpy of water vapor. So, if we indicate H as the enthalpy of moist air, this will be given by H is equal to H A plus W H V, because in 1 kg of or with 1 kg of dry air there is W kg of moist air or moisture. So, this is the formula. Then if we write down separately the expression for H A and expression for H V, we will get the enthalpy of moist air. So, H A is equal to C P air into T, assuming that our datum for enthalpy calculation is 0 degree Celsius. That means, at 0 degree Celsius we assume the enthalpy to be 0, then we get this particular formula, and CPA, that is equal to 1.005, this is basically in kilojoule per kg, kilojoule per kg, degree centigrade or Kelvin, whatever, kilojoule per kg, Kelvin or degree centigrade also one can write. This is the value of Cp multiplied by T. Now, there is some difficulty in calculating Hv. How should we calculate Hv? That means, what I am doing, what I have done here, I have calculated the enthalpy Ha at a particular temperature T. I also need to calculate Hv at that particular temperature T. So, how should we do it? Let us look into the process. This is our TS diagram. All right. And our sample is somewhere here. our sample is somewhere here. That means, it is at a pressure P and at a temperature T, at a temperature T. So, this is actually P and T. At this point, we want to calculate what is HV. Our reference is somewhere here, 0 degree Celsius, if we take it as a reference. So, this is somewhere here. So, we can write T is equal to 0 degree C, this we can write. Well, now, if we see, if we imagine one process of energy transfer, one can think of that the sample of in the sample the moisture which is there, that was initially at 0 degree Celsius, then its temperature has been raised to this temperature T, which is nothing but the dew point temperature of the sample, all right. Because if the sample keeping the pressure constant, if its temperature is reduced, then it will condense at this point. So, the it is like this, the moisture in the sample initially it was at 0 degree Celsius, then its temperature has been raised to its dew point temperature. At the dew point temperature it has been evaporated, and here at the dew point temperature we are getting saturated vapor. Then this saturated vapor, its temperature has been raised from the dew point temperature to temperature T, all right. So, this is the process what one can think of is involved in while the moisture has attained an enthalpy HV. So, this is the process it could be thought of which is responsible for attaining the enthalpy HV. Then I can write HV is equal to H water into this temperature I am writing TD, dew point temperature, all right. H water into TD plus HFG at TD, because we know that latent heat of evaporation that also changes from I mean for the pressure and temperature it also changes, that means for different temperature it also changes. So, we can write that. Then I can write no, I have let me write it here. HV is equal to CPW, not HW, CPW into TD plus HFG at TD plus CP vapor T minus TD. This is what I can write. Okay. So, how many different constants I have to use? I have to use the specific heat of water, I have to use the latent heat of water which is again dependent on temperature, and I have to use the specific heat of vapor. If any sample is given, I have to use these three constants to determine what is its enthalpy. So, this process is bit cumbersome. Instead, what I can do is like this. I will draw the figure once again. So, this is actually T is equal to 0 degree C, this is our P T, and this we have called T D. Now, you see this is temperature and entropy. Now, you see our psychrometry application is at low pressure region, all right. And in this region the enthalpy, it is a very weak function of pressure, but it is a function of temperature. That means, what I mean to say, suppose I take 3 points at same temperature, this point, let us say A, B and C both are at same temperature, then their enthalpies will not be much different. So, I like to write enthalpies of A, B, C are nearly same. Okay. So, if it is so, then what I can do, every time without, I mean every time if I take different temperature, I have to take different values of latent heat of evaporation. So, instead of doing this, I can take this 0 degree C for the calculation of enthalpy. That means, I can take this route of calculation. So, in that case our H V will be H V, earlier I have written C P W T D plus H F G at T D plus C P V T minus T D. So, this was my earlier expression. Instead of it, I am now writing H V is equal to H F G 0 degree C plus C P V T, T minus 0, so T. So, this is much simplified, all right. So, here always I am using a constant value for HFG and also I am using only one constant, that is CPV.
So, this TD would be wet bulb temperature.
This is this TD is the dew point temperature.
No, this T, final T will be the wet bulb temperature.
No, temperature of the sample. So, what are you asking me is that what is this T? This T is the temperature of the sample, not the wet bulb temperature, it is the dry bulb temperature, all right. It is the dry bulb temperature. So, HV I have got by this formula. Please once again you note down that it is HFG at 0 degree C plus CPV multiplied by the temperature or dry bulb temperature of the sample. Okay. Now, I will put the values and I will ask you to remember them. So, this is 2501, okay, plus 1.88 into T, and it will be obtained, HV will be obtained kilojoule per kg, kilojoule per kg. So, HV is in kilojoule per kg.
So T can be in Kelvin or degree centigrade.
Yeah. So, T is in degree centigrade or Kelvin. All right. So, generally people write it 2500 plus 1.88 T to make it more simple or easy to remember. 2500 plus 1.88 T. All right. So, now we know how to calculate the enthalpy of moist air. So, enthalpy of moist air of moist air, enthalpy of moist air H is equal to then 1.005 T plus 2500 plus 1.88 T multiplied by W. All right. So, this will be the this will be the enthalpy of moist air. Okay. So, change in enthalpy for moist air delta H, that is equal to H2 minus H1. All right. So, H2 is equal to 1.005 T2 plus 2500 W2 plus 1.88 W2 T2 minus 1.005 T2 T1 plus 2500 W1 plus 1.88 W1 T1. So, one can write 1.005 T2 minus T1 plus 2500 W2 minus W1 plus 1.88 W2 T2 minus W1 T1. All right. Now, problem is that H that can be expressed as Cp delta T, all right. But in this case we can see that it is exactly not so. These are the other terms which are coming into picture. Okay. But there is some sort of a one can do one can do slight change in this equation, and with some approximation one can define specific heat for moist air. So, that can be defined. It is like this. H one can write H is equal to Cpv plus W sorry WCPV plus CPA into T plus W into HFG at 0. This one can write, and this thing one can write CPT, this entire thing if we call it CP. So, CPT plus W HFG at 0, this is actually 0 degree Celsius. So, this you can write, all right. This CPT is a composite function of CPA, CPV and W. Okay. So, you see that H, that is becoming the summation of these two, and here though temperature is appearing, here we do not have a temperature term. But as I have told that one can make some approximation, because generally the W is small and contribution by W is small. So, one can make some sort of an approximation, and with that approximation we can write Cp for moist air, and again this is approximately 1.0216 kilojoule per kg degree Celsius. So, if we use this value, then H 2 minus H 1 will be equal to 1.0216 T 2 minus T 1. But mind that this is approximate calculation, only for quick calculation we use this value, otherwise we use the formula which we have derived earlier. All right. So, this is how we calculate the enthalpy of moist air. So, I have shown you the detailed calculation, also the value which is used for quick calculation, quick estimation. All right. Okay. So, for practical calculation we can use this particular value. Now, with this again I will quickly sketch the psychrometric chart. So, psychrometric chart looks like this. Okay. So, temperature, this is in degree Celsius in this direction, kg per kg of dry air in this direction. Okay. This is the sample here, sample point, okay. And in the sample point we have got, we can have constant enthalpy lines. H is equal to constant. Basically what is done in most of the psychrometric chart, one scale is provided over here. So, there the values of enthalpy is written. So, from the sample we can take a line, go up to that scale and find out what is the enthalpy. So, we can write scale for enthalpy. All right. Now, what is important or what is interesting to note that in a psychrometric chart we will have also constant wet bulb temperature lines, all right. Now, you will find that constant wet bulb temperature line and constant enthalpy lines, they are almost coincident. There is a very small angle between these two lines, they are almost coincident. Okay. So, I mean if we move along a constant wet bulb temperature line, we will find that enthalpy change is very small. If there is a constant wet bulb temperature process, if any process is there which is constant where the wet bulb temperature does not change, then we will see that change in enthalpy is also negligibly small in that process. What I am telling, is it clear? I mean to say initially my state point is here, finally my state point is here, all right, 1 and 2. So, you can see there is lot of change in temperature between 1 and 2, there is lot of change in specific enthalpy or specific humidity or humidity ratio between these 2 points, but these 2 points I have taken such that they are lying in the constant enthalpy line. Both of them are situated on constant wet bulb temperature line. So, I will find that the change in enthalpy between 1 and 2 is negligibly small. If they are on the constant wet bulb temperature line, then change in enthalpy between 0.1 and 2 is negligibly small, all right. One hint can be given here. You see between 1 and 2 what has happened? Let us say the process goes from 1 to 2. So, basically when it has gone from 1 to 2, then there is a decrease in temperature, is not it? Dry bulb temperature has reduced. What does it mean? When the dry bulb temperature can reduce? If it is cooled, if certain amount of energy is extracted from it. But we can see that there is a considerable amount of increase in the specific humidity when it has gone, when the sample has gone from state 1 to state 2. That means, moisture has been added, and when moisture has been added, then obviously certain amount of latent heat of evaporation that has also come along with the moisture. So, energy has been added. So, both these balances each other, one is extracted from it, another is added to it. So, both of these things, these two things, they balances each other, and that is why we will get almost negligible change in enthalpy. So, enthalpy of the mixture will remain almost constant. Okay. But not exactly, because there is a small angle of deviation between the constant enthalpy line and the constant WBT line, wet bulb temperature line. All right. Should we move to some other topic? Now, let us go for different air conditioning processes or different psychrometric processes. Okay. Now, what could be different processes? Let us say the central point is called O, and let me give different names A, B, C, D, E, F, G, H. So, these are different processes, these are different possible psychrometric processes. Okay. And you can identify the processes. See, let me put some arrow mark here. So, what are the different processes I have drawn? OA, let us say process OA. OA is what? Okay, let me put this degree C, this is kg per kg of dA, dry air. So, OA is increase in temperature, but there is no change in W. So, this is called sensible heating. OA is sensible heating. So, quickly let me give all the names, or let us identify all the processes. OB is sensible cooling. Okay. Then OC, that is addition of moisture, okay, and keeping the temperature same, okay, addition of moisture. And you see, by addition of moisture, though the dry bulb temperature remains constant, wet bulb temperature increases. See, through O, if I send some wet bulb temperature line, it will be something like this. But through C, if I send some wet bulb temperature line, that will be quite high, and wet bulb temperature has increased. Okay. Yeah, whatever it may be, sweating will take place, or we will see that if there is any wet surface, we will have difficulty in drying it up. All right. And OD is condensation process, okay, purely condensation process. Then there are mixed processes, like if we go for OE. So, this is heating plus humidification. OE, we have got heating plus humidification. All right. If we go for OF, we have got cooling plus dehumidification, cooling plus dehumidification. Then if we go for OG, then we have got cooling plus humidification, and finally, if we have OH, then we have heating plus dehumidification.
OC is cooling plus humidification.
OC, no, OC is purely humidification, addition of moisture, pure only humidification. There is no change of dry bulb temperature. Wet bulb temperature is changing, but dry bulb temperature remains constant. OF, cooling and dehumidification. Cooling and dehumidification is a very important process, because in summer air conditioning we need to have cooling plus dehumidification. We need to, the surrounding air we need to cool it, particularly for tropical countries, we need to cool it, and hot and humid atmosphere we need to cool it, and we need to also lessen the load of moisture from the air. All right, we will see how to do it. So, these are the basic psychrometric processes, and there are methods of achieving it, and there are small amount of mathematics which can be used for analysis of all the processes. But there is another process which has not been shown here, which is very important. Adiabatic mixing of two moist air streams. All right, adiabatic mixing of two moist air streams. All right. So, this is a very useful and important process. We can have number of examples like in air conditioning. Let us say the room air that is coming out. What we do? We do not throw away the entire of the room air into atmosphere. Part of it is thrown out and part of it is recirculated. Then with the recirculated air, we mix certain amount of fresh air. So, here we can see that two moist air streams are mixing together. What we want to do? We want to find out the property of the mixed air stream, knowing the property and mass flow rate of the individual air streams. So, it is like this. Let us say I have shown some sort of a ducting which has got two inlets and one outlet. So, this is m dot 1 mass flow rate, m dot 2 mass flow rate, and this is m dot 3. Okay. So, total mass flow rate, of course, if there is no condensation inside, if there is no separation of water vapor inside, then one can write m dot 1 plus m dot 2, that is equal to m dot 3. This is what we can write, and one can write, let me for the time being remove the dot, because but it indicates the air flow rate, whatever I am writing mass flow rate, that is flow rate, not the total mass. So, m A 1 plus m A 2, that is equal to m A 3. Dry air from stream 1 plus dry air from stream 2, that is equal to dry air from stream 3. This we can write always, but the second one, that is W 1 m A 1 plus W 2 m A 2, that is equal to W 3 m A 3, we cannot write always. We can write only when there is no separation of moisture. Okay. When there is no separation of moisture, we can write it. So, if there is no separation of moisture, if there is no condensation, then W 3 is equal to W 1 m A 1 plus W 2 m A 2 divided by m A 3. So, this is how we will get the moisture content of the mixed stream. Okay. Neglecting the changes in neglecting the contribution of kinetic energy, potential energy, etc., one can write MA1 H1 plus MA2 H2 is equal to MA3 H3. All right. So, this is actually energy equation. So, enthalpies are written here, and what we can do, we can express it in terms of different changes in enthalpy, that means enthalpy of air and water vapor, that is what we can write, and then we can actually we can write like this: Cp into T3 plus HFGO W3 is equal to MA1 by MA3 CpT1 plus HFGO W1 plus MA2 by MA3 CpT2 plus HFGO into W2. So, this is what I can write. This formula I have already introduced. Cp means the mixture specific heat, and here the air specific heat and water vapor specific heat, that will come. Okay. So, that way it has been written. Now, what we can write, if we want to make it little bit simplified. So, MA1 T1 plus MA2 T2 divided by MA3 plus HFGO by Cp, and here we will have MA1 by MA3 W1 plus MA2 divided by MA3 multiplied by W2 minus W3. This will be the expression. Now, what happens? Generally W1, W2, W3, these are very small quantities, and one can have an approximate expression for T3. So, one can write T3 is approximately, not exactly, but approximately MA1 T1 plus MA2 T2 divided by MA3. I will stop here, and next day I will show what is the implication and how the process can be represented on psychrometric plane. I think that is all for today. Thank you.